Thank you so much. Well, thank you very much for the opportunity to talk. It's the end of the day, but luckily this is going to be far simpler than everything else that has been presented today. As I wrote this yesterday, I felt like I should start by a little disclaimer because this sounded like a bit of a self-sales pitch, so you'll understand why later. I'm really sorry if it sounds like this. I don't earn money of anything I'm presenting today, but yeah. So the reproduction number RT, and I'm not going to address this question of what I'm actually talking about really, but it's great now. Everybody in the room obviously knows what RT is. Everybody in the world now knows what RT is the average number of secondary cases infected by each case. And I'm going to stay vague and say at time t. Why are people obsessed about RT or hate it at the same time? Because it's easy to interpret. So when RT is larger than 1, the epidemic is likely to grow, and when it's smaller than 1, the epidemic is declining. And it can be a really useful number to estimate at different stages of an outbreak. So initially, to try and predict what the potential impact of the outbreak is going to be. So if your reproduction number is higher, you can expect more cases, things like that. Also to assess the feasibility of control measures. So if you've got a vaccine that's got 70% effectiveness, what can you expect it's going to do if your reproduction number is that much? That the impact will depend on the reproduction number. Later in the outbreak, it's a useful quantity to measure to track potential changes in transmissibility over time. For example, if you've got a new variant or people starting to go to the pub, and also to evaluate the effectiveness of control measures that you might have implemented. There's actually tons of literature on the reproduction number, and I'm just going to refer to this review paper, which is talking about different definitions of the reproduction number, which is why I'm staying vague, because it's explained all in there very nicely. They also go into much more details about why it might be interesting to estimate each of those types of reproduction numbers at different stages of an epidemic. So I'm not going to do that. But I will ask the question, why should we care? And the reason I'm asking this question is because I've been working on the reproduction number for many years. And yeah, people keep asking me what, to estimate the reproduction number. Policymakers want to know what the reproduction number is. And at the same time, they tell me that they don't care about the reproduction number. So here are some of the things that I've heard over the years, which I think are valid from some perspective, but also maybe not so much. So the first one is typically healthcare workers telling me, why should we care about the reproduction number? We know when cases are going up, and we know when we're going to be overwhelmed in a hospital, basically. People have been telling me they draw an epidemic curve on a whiteboard and then it goes up and they just do this, the rule thing, right? And that's the rule thing. And it's just basically, as good as any of our models. A maybe more kind of formal way of saying this is actually the growth rate is more informative or is enough. And many people have been telling me this. So yes, I agree that growth rate is informative because it tells you how fast cases are growing or declining. So it tells you things like, when are you getting, probably in the short term, when are you going to hit a wall? But it also isn't that informative because it doesn't tell you how much effort is needed for control. So this is a really, really stupid, completely schematic, not to scale example, where you can see 2 epidemic curves which are completely identical, which have exactly the same growth rate. But this one comes from a sort of flu-like pathogen with short natural history and a relatively low reproduction number. And the other one comes from a more maybe measles-like natural history, so slightly longer time between generations of cases and a slightly higher reproduction number. By the way, this is not the reproduction number of measles. So when I talk about natural history, I'm thinking more time between generations. So these look exactly the same. They have the same growth rate, but really they don't mean the same at all, right? This one we expect to peak at a much lower level, for example, than this one. And in terms of control, here, what this tells me is that I need to prevent 9% of onward infection, whereas in this one, I need to prevent more than half of onwards infections. So this is my argument for why the reproduction number is still something that is important to characterize on top of the growth rates, which can tell us something. So there's many ways you can estimate the reproduction number, and it's impossible to be exhaustive. So here are some ways that you might go about doing this. You can do contact tracing, and this is basically trying to measure empirically what the reproduction number is. You can, if you can't actually, do contact tracing, you could reconstruct this statistically, the transmission tree. So basically inferring who infected whom based on data on the cases you're observing, epidemiological data, but also if you have some genetic information about the pathogen they carry. There's loads of methods to do this. We've heard a lot today about very complex mathematical models, individual-based models, but also compartmental models. And you can use some of those more mechanistic approaches to try and fit them to epidemiological data, and then infer the reproduction number from the underlying parameters. You can also fit models to genetic data, and that can also inform, so basically kind of like an analysis of phylogenetic trees with some assumptions about the process that generated those can also allow you to estimate the reproduction number. I feel like there is an excellent slide earlier on, which I'm kind of going to go exactly in the pitfalls of, to say all of this is very complex. Yes, I think, building an individual-based model is maybe not as complex as we think, but it is actually complex. Some of those issues, some of those methods suffer from the same common issues. So they can be expensive, they can be not really easily scalable. So manual contact tracing, for example, as we've experienced recently, is really not the way to go. Some of them can't be applied in real time because they require information and data that we haven't seen yet, that is only going to appear in the future, or just because they take too long to develop from scratch, of course, but even from kind of like pre-existing models. And I'm also going to say some of those models require many assumptions about the population in which the pathogen is spreading. So what's the population size, what's the population structure, what's the level of immunity in that population, and obviously hypotheses and assumptions about the pathogen, how it's transmitted, etc. So because of all of this, and because I'm really tired after 2 years, it feels like two decades and 2 years and 2 weeks at the same time. I'm really tired, I'm really lazy, and so I just want to go for a very simple model. The reproduction number can be estimated using a very simple model where the inputs are just the incidence data and assumptions about the serial interval. So the serial interval is the time between symptoms in a case and symptoms in their infector. And this is picture I actually draw when I was writing my PhD, but I think it's a nice illustration of how, if you have an observed incidence time series, which obviously never looks like this, but okay, and you have an assumption about the serial interval, you can basically look at how many cases you had at the start of a serial interval, at the end of it, do the ratio, and that will give you the reproduction number. And this is a very stupid diagram, but it's basically what we've implemented in a method that we published almost 10 years ago now, which we called the EpiEstim method. And this takes two inputs, so very simple, an incidence time series, so number of new cases over time, and the serial interval distribution, which, as I think Roz and others have kind of explained, can be quite hard to characterize. Nevertheless, we only have those two inputs, and then we feed that into a very simple model, which you may know as the renewal equation, which basically just says new cases appear because of past cases who are still somewhat infectious and have a current reproduction number RT. And we did a bit of sort of analytical work so that actually this simplifies very nicely, and within seconds of inputting those sort of inputs, you can get estimates of the reproduction number over time. And we've implemented this in an R package, but also in a Shiny app and in an Excel spreadsheet, so that various people who use different tools could use it. And so, yeah, I did this as my first postdoc 10 years ago, and then people just come to me and they're like, but this is really simple. Like, we don't model airflow circulation in this room. We don't model people going on the bus. We don't model a lot of things. So yeah, it is very simple, but actually it works well. So this is where, apologies for the self-sales pitch. But others, people, I wasn't involved in this, I was on maternity leave at the time, looked at comparing different methods for real-time estimation of the reproduction number at in the early days of the pandemic. And they actually found that this method works quite well and recommended that this should be used over other methods that were available at the time. And actually, just people use it. So this is like citations of our paper, and you can see a very clear COVID effects there, but also outside of academia. So a lot of policy public health agencies throughout the world are actually using EpiStim to monitor SARS-CoV-2 transmission and publish updates of what is RT in my country. So it's been used a lot. But people might use it and it might still be bad. So I'm going to ask the question: is it too simple? It is simple. Is it too simple? So one thing we did during the pandemic, which I'm going to skim over, but so us and other groups, and Matt has presented a lot of that amazing work that they did. We had a group at Imperial also working on trying to model the SARS-CoV-2 epidemic in England over the course of the pandemic in real time. And we had, at some stage in 2020, the model looked like this. It was very, very dynamic as maths. I think actually you have to times this by 7 because this was a regional model. And so it was what I would call relatively complex, 700 compartments times 7, whatever that is. Less complex than some of the models we've seen this morning, but relatively complex. And so when we published this paper, reviewer 2 asked us, okay, what is the reproduction number you're getting? Is that similar to what you're getting with very simple models? So we did that comparison using time series of deaths rather than infections, because obviously you don't observe infections, and rather than cases, because that was obviously biased by testing, which varied a lot over time. So here you can see the blue line is the reproduction number we got out of this model, which had many compartments, many parameters, and was fitted to very many different sources of data. And in yellow is the very simple model fitted only to the death time series, basically. And you can see, they differed a little bit, especially early on here. But overall, they were quite consistent. People also argue that this is a very simple model, and because it's not mechanistic, it can't allow exploring the impact of intervention. And although this is true in the sense that we can't do the same sort of very detailed scenario modeling as you can do with this sort of model here, you can still use it to assess to some extent whether some interventions might be effective or not, as long as you record information about interventions, which is an aside, but very, very, very important. And I'm not sure we're doing a great job at doing this. So this is work we did during the West African Ebola epidemic, where we used EpiStim to estimate the reproduction number in different months and different districts. So each bubble here is a district in one of the 3 mainly affected countries. And we compared the estimated reproduction number with 2 things. So one was the monthly proportion of cases who were hospitalized soon after onset. And the second thing was in that month and in that district, the proportion of people who reported they went to a funeral. And so we actually were able to quantify the relationship between those 2 known risk factors of Ebola transmission and the reproduction number. So this meant, we could kind of like have some targets, for example, for how many people we should aim to have in hospital within 4 days of their symptoms in order to bring the reproduction number below 1. Of course, this is all univariate, very, very simple, but it can still be used to explore interesting questions around interventions. So maybe I'm going to argue that such a simple model is best used in combination with other more complex models, which we, are fitted to more data sets. We've heard how, if you're using different types of data that have different types of biases, this is going to be more robust. And really, this is what has been done in the UK. So I think you'll hear from Louise maybe tomorrow a bit more about the SPAM process. But basically, different modeling groups were asked to produce reproduction number estimates on a regular basis, and those were then pooled and then used to inform policy. However, more complex models take time to develop, and I would be interested to know how many are still going to produce estimates, on a regular basis, because I think they're going to be the first ones to be dropped as we get out of the most acute phase of the pandemic. So I think it might be useful to have simpler models in there that you can rely on when the more complex models are not there. Another thing is it's really beneficial to have such a simple model because you can add features pretty easily whilst keeping the model and software simple and fast. So this is some of the work that I've been working on in the last few years, trying to add features that I thought were interesting or important. So this is work that was led by Robin Thompson, who's now in Warwick, looking at whether we can use EpiStim whilst using the latest data informing the serial interval. So here we're showing basically how if you assume a single serial interval distribution, which is typically informed from the first few cases in the outbreak, you're going to get very narrow confidence or credible intervals on your estimates, whilst if you allow for uncertainty around it, you're going to see that you were really overconfident. And here you can see how if you update your estimates of the serial interval in red with the latest available data, you're going to get a completely different picture potentially compared to if you're using the same serial interval you were using at the beginning, which we tend to do. So this can make a large difference in our estimates, and so we've implemented this within EpiStim so that you can do that now. We were also interested in knowing whether ignoring heterogeneities between different types of people in their serial interval might matter in terms of using such a simple representation of all people being the same, basically. And so we've done some work showing that indeed not accounting for those heterogeneities can bias your estimates, but it really depends on what sort of heterogeneity you're looking at. So looking at isolating versus non-isolating people doesn't really matter, but if you think of symptomatic and asymptomatic and you've only characterized the generation time for symptomatic people, that might be problematic. Similarly, if you've got vaccinated and unvaccinated who have different generation times and you've only characterized the generation time for vaccinated and for unvaccinated, individuals, that can be problematic. So it really emphasizes that it's important to characterize the serial interval of an average transmission pair, whatever this is at a stage in the epidemic. We heard about new variants and loads of different groups use their very complex models to try and estimate what was the transmission advantage of alpha when it first emerged, and then delta, and then omicron. And then I was thinking, well, actually, this is just a very, very simple extension of EpiStim. So maybe we can do that in a way that someone could just click on a button on a software and get an answer. So we did that. And again, we did a little bit of math so that we would rely on analytical results where it was possible, so that the software still is fast. And this allows exploring spatiotemporal heterogeneity in the transmission advantage. So this is here an example of estimating the transmission advantage of alpha over wild type over time in using UK data, and this is looking at different regions. And so because it's so fast, you can reapply it as many times as you want to look at different times, different spatial units, and then you can pull information where relevant to get your one estimate of what is the transmission advantage. So we use that retrospectively for alpha and then prospectively for delta and omicron, just because the software was there and we could just use it very easily. Of course, again, this is just a very simple method, and it only estimates the effective transmission advantage. So it doesn't tell you whether the advantage comes from an immune escape property or it's a genuine transmission advantage or a combination of both. But I think it's a useful first step in quantifying threats coming from new variants. Again, I might skim over this, but we had loads of people telling us, can I apply this to coarsely aggregated incidence data, so say weekly data, and we couldn't until recently. So one of my PhD students has been working on extending EpiStim so that you're analyzing, say, weekly or bi-weekly data, and you can actually reconstruct jointly the daily incidence and estimate the reproduction number. And the short story is that it works quite well. This this is looking at COVID, and if you aggregate and then disaggregate, you get sort of the same estimate of the reproduction number as if you assume you had only the weekly data. And you can see here on flu, where you have massive weekend effects with very few cases at the weekend, how your estimate of the reproduction number is very different if you look at the reconstructed data versus the true data. So this is weekly R and this is daily R, where obviously it's massively different, but where actually I would trust more the one coming from my reconstructed data than the one with the weekend effect. So that might be useful for when we get out of the acute phase. And for example, in the US, some states have stopped reporting COVID cases or COVID death every day, and they only do at a weekly time step. But also when you do have a lot of administrative noise like this, it might be useful. So I was also interested in what others have done, and so I'm going to go quickly because I'm running out of time, but just to say we did a quick literature review and small EpiStem user survey to understand what people have done. They've used it for tons of different things, COVID a lot, but also other diseases because it's so simple and generic. They've also expanded on the method quite a lot to do different things. And we found, for example, a lot of them were interested in adapting it for coarsely aggregated incidence data, as I've just said, but none of the software we found in our review was addressing this, which is why we thought we should do it. And maybe my final point is this here, we looked, so when we found software that was implementing improvements to EpiStem, basically, we looked at how usable it was in terms of how easy it was for us to install it, how documented it was, and how fast it was at our estimation. Because if it takes a week to estimate R, SPI-M is already like 20 steps ahead of that, and they don't care anymore. And we found that very few actually ticked all of the boxes here. So I think there might be an epidemic of methods and software, which might be good, but there is a lot of what I think from my like high school biology is called homoplazy. So different people doing the same thing, improving the same things in the software, but separately. I'll say many methods are not implemented in easily usable, ready-to-use software, and that prevents from actually using them. And very importantly, there's little systematic comparison of the performance of all those methods or guidelines on, when one should use this software or this method or that software. So I think this is very important. We need to have a strategy for method and software development, and I think this is a good platform to start discussions around this. I think we need to compare the different methods and think about what's worth the effort or not. So if you add a feature, but it means your software takes 3 days to run, maybe it's not so useful. So having that thinking, I think, is important. Perhaps thinking about implications for forecasting. So often R is used as an ingredient for forecasting. And then finally, I think even simple models have a place, a role to play in retrospective analysis, again, to test hypotheses. So for example, are there locations that are at high risk of epidemic, no matter what? This is, again, a plot from my PhD, looking at a correlation between the reproduction number for pandemic influenza in 1889 and 1918 in US cities. So suggesting there are factors that make a city more likely to do this. So you could do that with very simple models. I'm going to end here, but just maybe say that most countries do not have SPI-M, with tons of amazing modelers producing amazingly complex modeling. And although that modeling is also useful, I think simple ready-to-use tools are critical, especially in the early days, but also as a benchmark. So, is my super complex model doing something sensible or not? R is great and important, and I love it, but it really doesn't tell you the whole picture. It doesn't translate directly into burden. So all of the other things that people have been talking about today is also really important. Sorry for being long, and thank you so much.
So I wanted to ask, it seems a lot of the estimates there are floating around the value 1, right? And obviously it's a pretty big deal whether it's 0.9 or 1.1. I wonder if you had an insight into why that was. Is there some other feedback going on that is holding the time series in a pattern look like R is the one. That's the summary.
I mean, R isn't huge, obviously, for Ebola, and as you can see, so the bubbles here represent actually. I think the bubbles represent the weight those points so a district month has in the regression, because some district months had very little data and therefore uncertainty in R was huge. Uncertainty in the explanatory variable was also huge, and so we tried to account for both of those. And so because uncertainty was huge and numbers are around 1.5, you get to 1 pretty easily within your confidence interval. I don't know whether there is an inherent reason for that, and I agree it'd be important to kind of look at that. I think to do that well, you'd have to look at a multi-variable analysis. So here, this is like a one-way regression looking at the impact of this, and then we looked at that, but obviously you'd want to look at several things together. I just don't know how to do that well whilst accounting for uncertainty in each of those things which you're looking at. So yeah, but I think that would be something really interesting to look at.
Thanks. Great talk. I completely agree about simple models being incredibly useful in all of this. But I've got a question, and maybe I ought to talk to Robin as well about this. When there's two components with this, which is how much data have you got and how much have you got on the serial interval. I'm just wondering how much sampling do you need to do to get a really good estimate of that serial interval, and sort of how important is the tail? So do you actually need to know about the very, very small numbers that in this case have got 50 days rather than the average of 10?
Yeah, that's a really good question. I don't think we've actually thought about that. So I should have said this was using Ebola data. So obviously the red curves here show you the uncertainty we had as of a late stage in the epidemic, which I can't remember the date of, and the blue one was using really the very few first cases, maybe like I want to say a few tens, like 20, 30. So you can see how, you accumulated information. But yeah, it's a good question. When is the good thing? I would argue though that it's not. So there are two questions. There's a question about the sample size, basically, but there's also a question which has been highlighted quite nicely during COVID by Ben Carling and colleagues about the serial interval might change and will change because you're putting in interventions. And so that's yet another reason to maybe not even use all the cases since the start to characterize the serial interval, but to continuously use the last N cases where N is the sample size that Matt will publish in his next paper. I'd also highlight that we focus here on the uncertainty in the serial interval, which is one of the two ingredients. But obviously, if you don't have a good idea of what your incidence time series is like, you also get wrong estimates of reproduction numbers. So yeah, only two ingredients, but loads of opportunities to get it wrong.
Sorry.